Okay, folks, I just wanted to get you to have a little look at this simulation. It's the third one along, friction. We'll use this simulation for other things in the future, but it's got quite a nice little demonstration of how Newton's third law works as well. So if you leave the speed unchecked for the time being, if we just consider this box sitting on the ground, it has a mass of 50 kilograms, so it's going to have a weight of 500 newtons. Weight equals mass times gravitational field strength on whichever planet you're on. Most of the time that's going to be planet Earth, and that's 10 newtons per kilogram. So 50 times 10 equals 500 newtons. So right now this box, if you can imagine, it has a force arrow pointing straight down with 500 newtons written next to it. Because the box isn't going anywhere, and because of Newton's third law, the force from the ground pushing back up on it must be 500 newtons. You all seemed pretty happy with that when I was looking through your answers for things like the book on the table. The book pushes down on the table pushes back on the book. The scales on the floor, the scales push down on the floor pushes back up on the scales. I think some of you got a little bit confused when things like the book was pushing down on the table and the table was pushing down on the floor, or you were standing on the scales. What's the force between the floor and the scales? To sort of demonstrate it, let's who should we pick? I'm going to pick another box just to be simple. So now we've got a box of 500 newtons on another box of 500 newtons on the floor. So the force just from this box now hasn't changed. It's still a 50 kilogram box, a 500 newton box pushing down on the ground, but now you've got this extra box pushing down on it. There is a force between our top box and our bottom box, and that force is equal to the weight of the top box pushing down onto this box. So you've got 500 newtons pushing down from this box onto this box, and 500 newtons from this box pushing up as the equal and opposite force reacting to this box being on top of it. Now, the extra bit that's happening now is because this bottom box has also got this box on top of it, you've got 500 newtons pushing down onto this box. That adds together with the 500 newtons from this box pushing down into the ground. So there's not just a reaction force from the ground of 500 newtons anymore, it's now 1,000 newtons or a kilonewton pushing up against these two boxes. Because the ground cannot push this box separately, it's got to push up through both boxes. And you've got to feel for this. You know that this must be true, even if you're looking at it going, oh my god, that's so weird, I don't understand this at all. If you walk around carrying a very, very heavy backpack, your feet will get tired quicker because your body is having to hold up more mass the entire time. You don't feel just as light as you normally do when you're carrying a big full backpack. And you don't go anywhere, you don't start collapsing through the ground, so the ground must be pushing back up with the same force that you're pushing down onto it. It just happens that because you've got a big heavy backpack on, you're pushing down with a greater force. So the ground must be pushing back up with a greater force. Unfortunately, this simulation doesn't show the weight arrows and the reaction arrows because that's not what this simulation is about. It's about friction. But if I click on the little stick man and move it to one, sort of like apply a force to one side, you can play with this simulation at some point. You just click on the stick man and drag, and as I drag to the right, you can see the force increase. When we push to the right with a 50 Newton applied force, the box isn't going anywhere, so there is a 50 Newton force pushing back. Now, the way that's written is applied force versus friction force. That's what's happening sort of down here, where the box is interacting with the surface. But you can also think of it as what's happening where the stickman is pushing up against the box. So you could have a pair of force arrows down here for applied force and friction, and you could have a pair of force arrows right at the point where the stickman is pushing against the box with applied force and reaction force. It just happens that because nothing's moving anywhere, the friction force must be equal to the reaction force. And because the friction is set at a medium sort of level, as you push harder, the friction force increases as well. The friction force has got to increase up until the point that the box starts moving, in which case, at which point things get a little bit more complicated. But while we increase the force applied to it, the force that the box is pushing back with must be the same because nothing's moving anywhere. As soon as it starts moving, like that, you've got an imbalance of forces. Now that's not Newton's third law, that's Newton's first law, which is why it's starting to move faster and faster and faster to the right. There are still equal and opposite forces everywhere. It's just that those arrows aren't showing everything. So where those two arrows, there we go, where those two arrows became imbalanced, that's not violating Newton's third law. There are still there is still a equal and opposite forces acting everywhere. It's just not showing all of them. So yes, hopefully that has fixed some of the issues that it seemed like you were having. As I say, have a little play around with this. You can increase the friction so it's very, very high, so you have to apply a really massive force before it starts moving, at which point it does start to move. Or you can decrease the friction to absolutely nothing at all. So if you just push it ever so slightly, it starts moving, and it will just keep moving because this doesn't simulate air resistance. We've applied a little force. We've now taken the force away because we don't have a resultant force acting on it anymore. The motion can't change, so it's just going to stay moving at 0.1 meters per second forever now until the simulation breaks down and the little stickman falls over again.